Hi everyone, this is Dr. Sandeep, working as Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about the polymorphous and allotropy. So what is polymorphous? So we have different types of materials in which we have normal normal type of bodies as well as these polytropy or allotropy. So what is this polymorphism? So here most of the metals will have single properties, but some metals will have more than one property. That means because of the increase in temperature, one metal may change its properties or the atomic structure at different temperature levels. That means an element or a metal may have two different types of atomic structures. That type of metals are called as polymorphous materials. So what is happening here? If you see the definition, some metals as well as non-metals may have more than one crystal structure. This phenomena is known as a polymorphism. So any material or non-metallic elements which is having more than one crystal structure, then that type of materials will called as a polymorphous. So as I said, depending upon the temperature, suppose the carbon atom at normal temperature it looks like a graphite, and if you increase the temperature again it changes its atomic structure to another diamond. So that is the same metal is having different types of atomic structures at different temperature levels. So this type of phenomena is called as a polymorphism, and we found in metals, in solids, and this condition is termed as allotropy. Now what is the difference between the allotropy as well as polymorphism? Is the polymorphism is nothing but the metals or non-metals which are having more than one crystals, then that type of phenomena is called as a polymorphism. And what are the polymorphism we are seeing in solids, in metallic solids, and that type of phenomena is called as a allotropy. And the prevailing crystal structure depends upon the temperature as well as the external pressure. So how does this atomic structure is varying? Means it completely depends upon the how much amount of temperature you are giving as well as how much amount of pressure you are giving to the metals. Suppose if you increase the temperature from 100 degrees centigrade to 200 degrees centigrade, there may be some changes in the properties. So because of the changes in the properties, what is happening? The atomic structure also changes. So thus what is happening here? The same metal is having different types of atomic structure at different intervals of time. And similarly, if you apply the pressure on the element, on the metal, what is happening? At some particular pressure, the atomic structure will be the same. And of course, if you increase the amount of pressure again for the same metal, because of the high pressure, what is happening? The internal structure of the atoms will change. So thus the atomic structure completely depends upon the temperature as well as the pressure which are giving on the metal. So this is about the polymorphism as well as the allotropy. So polymorphism is nothing but the metals or non-metals which are having more than one crystal structure, and that type of phenomena is called as a polymorphism. And similarly, what are the polymorphism we are observing in the solid metals, then that type of phenomena is called as a allotropy. And if you see the best example which is found in the carbon atom. So what is happening here? Carbon is the best example to explain about this polymorphism phenomena. So the graphite is stable polymorphous at ambient temperature. So whatever the graphite atomic structure we are getting, so that atomic structure will be at the ambient temperature. So at ambient temperature conditions, we have the graphite atomic structures for the carbon. Now, whereas diamond is formed at extremely high pressure. So same carbon atom at ambient temperature, it acts as a graphite. So we have the graphite atomic structure for the carbon at ambient temperature. Now for the same material at high pressure rate, what is happening? It is acting as a diamond. So diamond atomic structure is formed for the carbon at high amount of pressures what we are applying. So the carbon is the best example to explain about the polymorphism mechanism. So at ambient temperatures, the carbon is acting as a graphite, and at high pressure conditions, the carbon is acting as a diamond. So these are the best example to explain about the polymorphism. Also, what is happening here? Pure iron has a BCC crystal structure. So, what is happening here? What is the pure iron is having? So, it has a complete body-centered cubic structure at room temperature. So, that's why whatever the structure is there, this structure is completely depending upon the temperature as well as the pressure. So, the BCC at ambient temperature conditions, it is having the BCC type of crystal structure, the pure iron. Now, what is happening? Slowly, it is changing to FCC, that is face-centered cubic structure at 912 degrees centigrade. So, if you're increasing the temperature rate, so what is happening here? The same pure iron, it is changing from BCC to FCC. So, there is some change in the crystal structures. For the same metal, it is having two different types of atomic structures at different temperatures. So, ambient temperature, the iron, pure iron is having a BCC type of crystal structure. Now, if you increase the temperature around 912 degrees centigrade, we are converting, we can see the conversion of the BCC to FCC, which is completely based upon the temperature conditions. So, most often, a modification of the density or the physical properties accompanies a polymorphism transformation. So, because of this polymorphism mechanism, what is happening? There is an influence in the mechanical properties as well as the characteristics of the material. So that's why the polymorphism is completely depends upon the how much amount of temperature you are giving as well as how much amount of pressure you are giving onto the material. So in this way, there are two best examples to explain about this polymorphism. What is happening here? The carbon at ambient temperatures, it is having a graphite type of atomic structure. The same carbon, if you are giving a high amount of pressure, so this graphite structure is changing to the diamond atomic structure. So this is how you can observe the polymorphism in the carbon atom. That means it is having two or more than two atomic structures. Similarly, the pure metal, the pure iron, what is happening? It is having the body-centered cubic structure at room temperature conditions. Now, if you increase the amount of temperature, slowly this BCC is converting to the FCC cubic structure because of the temperature variation. So, this is how the temperature as well as the pressures are impacting the type of atomic structures. That is how you are getting the polymorphism mechanism. Now, the crystal systems, if you see, because there are many possible different types of crystal structures, it is sometimes convenient to divide them into groups. So, we can't identify because you have n number of types of crystal structures. So, it is very easy for us to differentiate these types of cubic structures. So, based upon the category, it is very easy to us to differentiate what type of crystal structure is having the material. So, based upon the unit cell configuration or the atomic arrangement. So, how the atoms are arranged. So, depending upon the arrangement of the atoms and depending upon the unit cell, you can easily distinguish these types of grouping systems. Why? Because there are huge number of crystal structures which are available. So, that is why these grouping or the characteristics or the characterization of these unit structures based upon the unit cell as well as the atomic arrangement. So, one of such scheme is called as a unit cell geometry. So, we are trying to bring out some unit cell geometry. Based upon the geometry of the unit cell, you can easily distinguish or you can easily find out what type of crystal structure it is. That is the shape of the appropriate unit cell, which is parallel pipe, without recording the atomic position of the unit cell. So, this is how you can easily identify what type of unit cell you have, what type of crystal structure we can have, what type of arrangement of the atoms are there. So, depending upon, by taking some unit cell from the complete origin, you can take a small unit cell and you can describe the small unit cell properties, then it is very easy to us to identify the complete atomic structure. So, we have to differentiate or we have to segregate these units into small element and you can find out the element properties of each atomic structure. So, how can we identify this? So, what is the framework for designing or for the geometry of these crystal structure means we have to have some origin. Why? Because based upon this origin only, we can easily distinguish at what distance along x coordinate, y coordinate, z coordinate the element is moving. At what, how much amount of distance. So, here, if you see the unit cell, it is having an origin at this point, and you have an x-axis, y-axis, and z-axis. These are the three coordinate axes for this unit cell. So, based upon these coordinate axes, we can easily tell what is the size of each unit cell. So this is how you have the three coordinate axis. These three coordinate axis coincides with each another. So all these three has to coincide of which each other, and also the parallel pipe edges. So what are the edges you have? Exactly, it is being in contact. So, and if you see the angle between these, this is the alpha, this is the beta and gamma. So these are the three angles between these three axes. Okay, and of course these are the edge lengths, axial lengths. That means along x-axis what is the distance, along y-axis what is the distance, and along z-axis what is the distance. So A, B, C are the three axial lengths along x, y, z direction. So what is the distance now? If you see along x, you have the distance A. Along y-axis, which is the parallel to here. So along y direction you have a B distance. Now along z you have C. So these are the axial lengths along x, y, z direction. So based upon this unit cell, we can easily identify how much distance a point is located in a unit cell. So this is a small unit cell what we are taking from the complete atomic structure. So we have a lot of atomic structures like this. So where internally each atom is connected, different types of cubic structures. So like this we have the atomic structure. So what we are trying to do, we can't completely find out. We are taking a small unit like this. We are taking a small unit which is referred like this, and this small unit which is called as a unit cell. So this unit cell has to established with its origin at one end of the unit cell. So at one end of the unit cell, so this is the one end of the unit cell. That's why we are having the axis. We are describing the unit cell in terms of these three reference axes. And what is happening again? These XYZ coordinate axis should coincide with one of the edges of the parallel pipe edges. So this is one of the important point. So in this way, you have to design a unit cell, and of course the axial lengths you have to describe along x, y, z directions. So these are the how the unit cell is being described. Now the unit cell geometry is completely defined in terms of 6 parameters. So what are the unit cell we are considering? It is completely depending upon the 6 parameters. So what are the 6 parameters we can see in the unit cell? So these 6 parameters are nothing but the axial lengths along x, y, z, that is A, B, C, and also the interaxial distance, that is the interaxial angles, alpha, beta, gamma. So here totally you have the axial lengths A, B, C, and interaxial angles alpha, beta, and gamma. So totally how much? 6. These are 6 parameters what we have. So if you alter one parameter, the complete orientation or the complete geometry of the unit cell will change. So this is how the unit cell is depending upon these 6 parameters. So any one parameter is altered, the complete geometry of the unit cell will change. So that's why the unit cell geometry is completely dependent upon these 6 parameters, that is A, B, C, and alpha, beta, gamma. So what are those? Axial lengths as well as the interaxial angles, and these are indicated in the figure. So you can see completely in the figure the A, B, C are the axial lengths, alpha, beta, gamma are the interaxial angles. Now on this basis, on the basis of these 6 parameters, we can try to bring out some different types of combinations with alpha, beta, gamma, and ABC. So completely 7 different possible combinations can be completed. So these 7 crystal systems are: first one is the cubic, tetragonal, the third one is hexagonal, fourth one is orthorhombic, fifth one is rhombohedric, and sixth is the monoclinic, and the seventh one is triclinic. So total you have 7 different combinations or 7 different possible combinations with these 6 parameters. When you alter, we can get the 7 crystal systems. So we will see one by one what are the different types of relations between these unit cell geometries with the 7 crystals. So first one, if you see, this is the crystal system. So here you have the axial relationships. So that is the what is the distance between these axial lengths, whether they are equally distance or there is some distance. So here you can see A, B and C are both three sides are equal to each other. That means the axial lengths along x, y, z directions, along all these three directions, all these axial lengths are equally distributed with each other. And also, if you check the angles, interaxial angles between the alpha, beta, and gamma, so all the angles are at 90 degrees with each other. So based upon these angles of 90 degrees with each other, and also the axial lengths which are equally distributed, that is A, B, and C are equally distributed with the same lengths, then you can get a unit cell geometry like this. Complete cubic structure you can get. All the sides are equal. Wherever you see, all the sides. So A, B, C are equal. That's why here A. That means A equal to B equal to C. And the if you see the angle here between the alpha and beta, you'll get 90. And if you check here, again you'll get 90. Again, if you check here, you'll get 90. So like this, all the angles, the interaxial angles are at 90 degrees centigrade, 90 degrees, and the axial lengths are equally distributed with each other. So same lengths. So that's why you're getting a complete unit cell geometry as a cubic crystal structure. So this is one of the cubic structure which is having the same lengths and same angle. So this is called a cube. The first relation. The second one is we are getting hexagon. So how we are getting hexagon means here A equal to B and B not equal to C. That means A and B are same and A is not equal to C and B is not equal to C. So if you have a relation like this and the angles now alpha and beta are same, which is 90 degrees, and gamma is 120. So in this case you are getting a hexagonal type of cubic structure. So this is the unit cell geometry. You can see here a hexagon type. So this is the hexagon. So this is the hexagonal geometry. Now the third one is the tetragonal. So how we are getting here, again A equal to B and B is not equal to C. That means again A equal to B, B equal to A, and C is not equal to A or B. So this is the relation. And again alpha, beta, gamma, all the angles are at 90 degrees centigrade, then 90 degrees, then you are getting a tetragonal type of crystal system. So this is the tetragonal crystal system where A and B are same and this A, B is not equal to C. And what are the interaxial angles? All the interaxial angles are at 90 degrees. So this is how you can get the third crystal system, that is the tetragonal. The fourth one is orthorhombic. So in this, what is happening? All the sides are equal. A equal to B equal to C. That means the axial lengths are equally having the same length. And if you see the interaxial angles, again alpha, beta, gamma are not equal to 90. So other than 90, any angle can be there. It may be 0 to 180 or above 110 to 180, like this. Different angles it can be, but it should not be equal to 90 degrees. So apart from 90 degree, any angle it can have. So this type of relation, if you change the parameters in this format, that is A, B, C are equally having the same axial length, and alpha, beta, gamma are not equal to 90 degrees, then you are getting a type of rhombohedral crystal system. So this is the fourth type of crystal system what we have. And coming to the fifth one, orthorhombic. Here orthorhombic, all the sides, that is the axial lengths, are not equally having the same lengths with each other. So A is not equal to B is not equal to C. So you have a different axial lengths, and of course the angles again are equal. The angles are alpha, beta, gamma. The interaxial between these three are equally having the 90 degrees, but the axial lengths are not equal. Then that type of system is called as a orthorhombic crystal structure. So this is the fifth type of category. And coming to the sixth category, you have the monoclinic. So monoclinic, again, all the sides, A is not equal to B is not equal to C. So different axial lengths you have. And if you see here, alpha and gamma are 90 degrees and this is not equal to beta. That means beta cannot be 90 other than 90 degree, any degrees it can be, but alpha and beta should be 90 degrees. 90 degrees. So if you have this type of things in the crystal system, we can get the monoclinic type of crystal system. And coming to the last one, triclinic crystal system. In this, what is happening? Again, A, B, C are not equal with each other. That is, the axial lengths are not equal with each other. And coming to the angles also, the interaxial angles, here also alpha, beta, gamma are not equal to 90. So other than 90 degrees, it can be any other angle. So this type of system is called as a triclinic. So totally based upon these 6 parameters, that is the A, B, C, that is the interaxials, axial lengths, and alpha, beta and gamma, that is the interaxial angles. Based upon these 6 parameters, so totally we are getting 7 crystal systems. So in this way, based upon these 6 parameters, what are the 6 parameters we have seen? That is the alpha, beta, gamma and ABC. So by changing any one parameter from these 6 parameters, totally we are getting 7 crystal systems. So these 7 crystal systems, what we have discussed, the first one is the cubic, the second one is the hexagon, the third one is the trigonal shape crystal system, the fourth one is the rhombohedric, fifth is the orthorhombic, sixth is the monoclinic, and seventh is the triclinic. So these are the 7 different types of crystal systems based upon these 6 parameters what we are trying to alter. Now if you see how to calculate the volume of an FCC unit in terms of atomic radius. So based upon the atomic radius, how to find out the volume of the face-centered cubic structure. If you see here, so we have the figure. Each atom which is in contact with the center, the face center, is having a radius r. So here also you have r. So this is r, this is r, this is r, this is r. So r plus r plus r. That's why you're getting 4r. Okay, so this is the figure what you have. This is the 4r, the side, and the length. This is a. So this is the right angle triangle what we are getting from the FCC cubic structure. Okay, so based upon this right angle triangle, we can find out what is the volume of this FCC based upon the atomic radius. Now you can see here the atom touches one another across the face diagonal of the length of 4r. If you see along the diagonal side, along this diagonal side, each atom is touching the face of the diagonal along this. So here you can see the face, here also you can see the face, okay, and here also, here also. So along this diagonal, if you see, or along this diagonal also see, you can see the 4r. So all smaller, here this is r, and of course this is r, and here you have r. So complete 4r. Along the diagonal direction you have a length of 4r. And because of the unit cell is cubic structure type of thing, the volume will be a cube. Not since it is a cubic type of structure, the volume of this cube which is having the sides as a, so the volume will be a cube. And where a is the cell edge length. So if you see here, the edge lengths are a. Now from the right angle triangle, so this right angle triangle, so this is the right angle triangle what we have. So this is 4r. And this is a and this is a. So from the right angle triangle, a square plus a square is equal to 4r square. So from this right angle triangle, what we are getting, a square plus a square is equal to 4r square. This is nothing but 4r is equal to root of a square plus a square. So, and by solving this equation, what we are getting, a is equal to 2r into root 2. Okay. So we got the a value. Now what is the volume of the this cube? That is a cube. So VC, that is nothing but the FCC volume of the unit cell is specified with the VC symbol. And since you have the volume as AQ, so this is the cubic term. So 2R root 2 whole cube, this gives to 16R cube into root 2. So this is the volume of the FCC in terms of the atomic radius. So in this way you have to find out. So first of all you have to know how much of each atom is trying to contact with the. So if you see here along the diagonal side, it is being contact with the 4 edges. So here you have the R and R and R. So totally you have the 4. The sides along the diagonal length you have the 4R. From this again you can draw the right angle triangle so that you can find out what is the distance along this right angle triangle. So you'll get this equation as a square plus a square equal to 4R square. So from this you can find out easily what is the A value. So what is A here? The volume A cube. So you can do the cubic term so that you can get easily the volume of the unit cell in terms of atomic radius. That is VC is equal to 16 R cube root 2 is the volume of the FCC in terms of the atomic radius. Similarly, if you want to find out the atomic packing factor for the FCC crystal structure, and you had to show it is a 0.74. So by definition in the previous classes what we have seen, the atomic packing factor is defined as the ratio of the volume of atom in unit cell to the total unit cell volume. So this atomic packing factor is defined as the ratio of how much volume of atoms are there in the unit cell, small unit cell, to the total volume of the unit cell. So this is how you can define the atomic packing factor, that is given by VC by VS by VC. So now, but the total atom of the unit cell can be calculated by the atomic radius. So what are the things we have calculated from the volume of the sphere? Since it is a sphere, the volume of the sphere is defined as 4 by 3 pi r cube. So you know the what is the volume of the sphere. So based upon the volume of the sphere, what we can do, since the FCC atom again is having a 4 sides, and 4 sides it is being contacting, so that's 4 times of its volume of the sphere, that is 4 into the volume of sphere. So what is happening here? 4 into 4 by 3 pi r cube. So you are getting 16 by 3 pi r cube. So this is the volume. Now whatever the volume we have calculated per unit cell in the previous problem, that is 16 r cube into root 2. Now we got the what is the volume per unit cell. Also, what is the total volume of the unit cell? So total volume of the unit cell of the sphere is 4 times of its volume, that is 4 into 4 by 3 pi r cube. And what is the volume of unit cell? That is recently we have calculated, that is 16 r cube into 2. So total atomic packing factor is the ratio between these two. So 16 by 3 pi r cube by 16 r cube root 2 gives to 0.74. So this is the atomic packing factor for this FCC. Now what is the importance of this atomic packing factor? So based upon the atomic packing factor only we can tell that how much atoms are closely packed, how much amount of percentage of these atoms are closely packed. So based upon the atomic packing factor, so what are the materials will have a good packing factor? That means you have a good strength, that is the bonding between the atoms is very, very high. If you have less atomic packing factor value, that means there is a weakness in the bonding between the atoms. So higher value, so by selecting any material for any application, you have to select a material in such a way that the materials should have a good atomic packing factor value. Then only that the materials will have a good bonding internally between the atoms. So this is the importance of the atomic packing factor. And coming to the density computation, so how to find out the density? How dense the atoms are closely packed inside the material can be given by this relation. So knowledge of crystal structure of a metallic solid permits the computation of its theoretical density relation. So theoretically we can find out the density relation based upon this density value. So density is given by Na by Vc into Na. So what is Na here? Number of atoms associated with each unit cell. So within the unit cell, with each unit cell, how many number of atoms are there associated with each unit cell? And capital A gives us the atomic packing factor, and V C, of course, the volume of the unit cell, and A is the Na is the Avogadro's number. So this is the theoretical value to find out the density of the material. So this density of the material can be compared with the practical value also, so that we can easily find out what is the difference between this theoretical as well as the practical value. So based upon the comparison between the theoretical as well as the practical value, we can tell the density comparison values of any type of material. So this is the relation to find out the theoretical density of any type of crystal structure. Now, if you see this problem, copper has an atomic radius of 0.28 nanometers, which is an FCC structure, and an atomic weight of 63.5 grams per mole. For this, you have to compute its theoretical density and compare the answer with its measured value. So here, what are the data is given for the copper. So this copper, you have to calculate the theoretical density value, and what are the theoretical density value we are getting. This theoretical density value we have to compare with the practical value, that is the measured value. Already it is being measured by some practical experiments. This experimental value has to be compared with the theoretical value for the given copper. Now, since it is a FCC type of crystal structure, so what is the number of atoms? In this case, you have 4 atoms since it is an FCC. So based upon the different types of atomic structures or the different types of cubic structures, we have seen these types of unit cells for each type of atom. So in this case, since it is an FCC, you have total 4 atoms in unit cell, and further the atomic weight is given as 63.5. So what the value you have written as here, the atomic weight is given as 63.5, and the unit cell volume, what is the volume we have calculated, is 16 into r cube root 2, and the atomic radius, of course, is given as 0.128 nanometers. So these are the values what we have. Now with these values, we will try to find out the density of the given copper atom of theoretical value. So this is the equation what we are using to compare the density value, that is NAU by VC into Na. So what is the N? N value is nothing but the number of atoms per unit cell. So since it is an FCC type of crystal structure, you have 4 atoms per unit cell. That's why it is written as 4 atoms per unit cell. And AU, the atomic weight of the copper, is given as 63.5, and VC is the volume, that is 16 root 2 into Na. Na is nothing but the Avogadro's number, that is 6.022 in 10 power 23 atom per mole. So if you calculate in this, you are getting approximately 8.89 gram per centimeter cube. So this is the theoretical value of copper. Now from the literature, the density of the copper is given as 8.94 grams per centimeter cube. So this is how the almost it is similar. We can see the value here. It is almost very close to the relation of the density of the copper for the practical value. Since what are the results we are getting is almostly correct. So this is how you have to compare the relation between the density calculations for the copper based upon the theoretical as well as the already measured value. So if these two values are very close to each other, then it is the whatever the calculations we have done is correct. So this is how the importance of the density calculations are very important to find out the properties of any material. So in this session, we have discussed about the type of what is the polymorphous material, what is the allotropic materials, and also how to find out the atomic packing factor when compared to the radius of the given FCC or BCC material, and also how to find out the density relation between the theoretical density and the practical density, and what is the importance of atomic packing factor also we have discussed in this session. So you can refer all these things from the references book like Introduction to Physical Metallurgy by Sidney Havner, and Essential of Material Science Engineering by Donald, and the third one is Material Science and Metallurgy by Kodigiri, and the fourth reference is Material Science Engineering by William Castle. So these are all the references books where you can find the information of the type of polymorphous materials, how the polymorphous is changing its different atomic structures based upon the temperature as well as the pressure conditions, and what type of pressures or how the material is being changing, and what are the solid materials which is having different types of atomic structures based upon the atomic variations of these structures, and also what is the importance of the atomic packing factor. So based upon the atomic packing factor only we can decide how closely each atom is present inside the material. So you have higher values of atomic packing factor, then it is very harder material when compared to any other type. So what are the materials we are selecting in the applications? We have to select a material which is having a high rate of atomic packing factor. And also we have seen the relation between the atomic packing factor and the atomic radius for the FCC type of crystal structure. And also we have tried to bring out the relation between the density calculations for the practical as well as the theoretical. Based upon these two values, if they are very close to each other, then what are the results we are trying to find out are very close, hence the results are proved. So this is the importance of the atomic packing factors values as well as the polymorphous materials. Thank you for this session.
Like, share and subscribe. Hit the bell icon for more updates.